Today's lesson will focus on decision trees and tree ensembles, two important concepts in machine learning. We will delve into the fundamentals and applications of these models. Let's begin our lesson on the next slide. Imagine you're a data scientist working on a complex problem, trying to make sense of a vast amount of information. You need a tool that can help you navigate through the data, make decisions, and ultimately solve the problem at hand. This is where decision trees and ensemble learning come into play. Graphical representation. Picture a tree-like structure with branches and leaves representing different paths and outcomes. Each internal node of the tree represents a decision point, where the data is split based on a specific feature. The leaves of the tree represent the final classification or predictions. This graphical representation makes decision trees intuitive and easy to understand, even for non-technical stakeholders. Construction building. A decision tree involves recursively partitioning the data based on the most informative features. The goal is to create subsets of the data that are as homogeneous as possible with respect to the target variable. This process continues until a stopping criterion is met, such as reaching a maximum depth or a minimum number of samples per leaf. Partitioning measures to determine the best feature to split the data on. Various partitioning measures can be used. These measures evaluate the quality of a split based on how well it separates the classes or reduces the impurity of the subsets. Common measures include Gini impurity, information gain, and entropy. The choice of the partitioning measure depends on the nature of the problem and the desired properties of the resulting tree. Decision trees: issues, pros, and cons. While decision trees are powerful and interpretable, they have some limitations. They can be prone to overfitting, especially when the tree becomes too deep or complex. This means that the tree may perform well on the training data, but fail to generalize to new, unseen data. Additionally, decision trees can be sensitive to small variation in the data, leading to instability. On the positive side, decision trees are easy to understand and visualize, making them valuable for communicating insights to stakeholders. They can handle both categorical and numerical data and require minimal data preprocessing. Decision trees also provide a natural way to handle missing values and can be used for both classification and regression tasks. Ensemble learning. To overcome the limitation of individual decision trees, ensemble learning techniques come to the rescue. Ensemble learning combines multiple decision trees to create a more robust and accurate model. The idea is that by aggregating the predictions of several trees, the ensemble can reduce overfitting, improve generalization, and handle more complex relationships in the data. Bagging. One popular ensemble technique is bagging, short for bootstrap aggregating. Bagging involves creating multiple decision trees, each trained on a random subset of the data with replacement. The final prediction is obtained by averaging the prediction of all the trees for regression, or by taking the majority vote for classification. Bagging helps reduce the variance of the model and can improve its overall performance. Boosting. Another powerful ensemble technique is boosting. Boosting works by sequentially building decision trees, where each subsequent tree focuses on the mistakes made by the previous trees. The trees are typically shallow, and the final prediction is a weighted sum of the prediction of all the trees. Gradient boosting machines, GBM, and AdaBoost are popular boosting algorithms that have shown excellent performance in various domains. Random forest. Random forest is a specific ensemble method that combines bagging with random feature selection. In addition to training each tree on a random subset of the data, random forest also selects a random subset of features at each split. This further increases the diversity of the trees and reduces the correlation between them. Random forest is known for its robustness, ability to handle high-dimensional data, and excellent performance in many real-world applications. In conclusion, decision trees and ensemble learning techniques offer a powerful and versatile toolset for tackling complex data science problems. By understanding their strengths, limitations, and how they can be combined, you can make informed decisions and create models that are both accurate and interpretable. Whether you're working on a classification task, a regression problem, or exploratory data analysis, these techniques are essential in your data science toolkit. In the realm of machine learning, decision trees have emerged as a powerful and intuitive approach to solving classification and regression problems. As a non-parametric supervised learning method, decision trees offer a unique perspective on modeling complex relationships between input features and target variables. At its core, a decision tree represents a model in the form of a hierarchical tree structure. This structure consists of two main components, decision nodes and leaf nodes. Each decision node represents a test or condition based on one of the input features, while leaf nodes represent the final predictions or classifications. The beauty of decision trees lies in their ability to learn decision rules directly from the training data. By recursively partitioning the feature space, the algorithm creates a series of if-then statements that guide the prediction process. These decision rules are learned through a process of splitting the data based on the most informative features, aiming to maximize the homogeneity of the resulting subsets with respect to the target variable. One of the key advantages of decision trees is their interpretability. Unlike some black box models, decision trees provide a transparent and easily understandable representation of the decision-making process. The learned tree structure can be readily translated into a set of if-then statements, allowing stakeholders to comprehend the logic behind the model's predictions. This interpretability makes decision trees particularly valuable in domains where explainability is crucial, such as healthcare, finance, and legal applications. By examining the decision rules, experts can gain insights into the factors that influence the model's predictions and validate the model's reasoning against domain knowledge. Moreover, decision trees are versatile and can handle a wide range of data types, including categorical and numerical features. They are relatively robust to outliers and can effectively handle missing values, making them suitable for real-world scenarios where data quality may be imperfect. However, it's important to note that decision trees do have some limitations. They can be prone to overfitting, especially when the tree becomes too deep or complex. Overfitting occurs when the model learns to fit the noise or idiosyncrasies of the training data, resulting in poor generalization to unseen data. To mitigate this issue, techniques such as pruning, setting maximum depth, or minimum samples per leaf can be employed to control the complexity of the tree. Another consideration is the potential instability of decision trees. Small variation in the training data can sometimes lead to significantly different tree structures, especially when dealing with high-dimensional or noisy datasets. Ensemble methods, such as random forest or gradient boosting, can help alleviate this instability by combining multiple decision trees to create a more robust and stable model. In conclusion, decision trees offer a powerful and intuitive approach to supervised learning. Their ability to learn interpretable decision rules, handle diverse data types, and provide transparent predictions make them a valuable tool in the data scientist's toolkit. By understanding the strengths and limitations of decision trees, practitioners can leverage their potential to solve complex problems and gain insights from data. As we delve deeper into the world of decision trees, we'll explore the various algorithms and techniques used for constructing and optimizing these models. From the classic ID3 and C4, 5 algorithms to more advanced variants like CART and CHOD, we'll uncover the intricacies of building effective decision trees. We'll also discuss the role of feature selection, hyperparameter tuning, and model evaluation in ensuring the robustness and generalization ability of decision tree models. So, whether you're a seasoned data scientist or just starting your journey in machine learning, embracing the power of decision trees can open up a world of possibilities in solving real-world problems and uncovering valuable insights from your data. When it comes to visualizing decision trees, the most common and intuitive representation is through an inverted tree structure. This graphical depiction allows us to understand the flow of decisions and the hierarchical nature of the model. Imagine a tree, but instead of growing upwards from the ground, it starts at the top and branches downwards. The topmost node, known as the root node, represents the starting point of the decision-making process. This node contains the initial condition or question that sets the stage for the rest of the tree. As we move down from the root, the tree begins to split into two or more branches. Each branch represents a possible outcome or decision based on the condition evaluated at the parent node. These splits are determined by the features and thresholds that the decision tree algorithm has learned from the training data. The branching process continues recursively, with each subsequent node further refining the decision-making process. At each level, the tree becomes more specific, narrowing down the possible outcomes based on the combination of features and conditions encountered along the path. As we traverse deeper into the tree, we encounter decision nodes and leaf nodes. Decision nodes represent the points where the tree poses a question or evaluates a condition based on a specific feature. These nodes guide the flow of the decision-making process, directing us down different branches based on the answers to the questions. On the other hand, leaf nodes represent the final outcomes or predictions of the decision tree. When we reach a leaf node, the tree has exhausted all the relevant questions and conditions, and it provides us with a conclusive decision or prediction. Leaf nodes are the endpoints of the decision-making journey, where the model's final output is determined. The elegance of this graphical representation lies in its ability to provide a clear and concise overview of the decision-making process. By following the path from the root to a leaf, we can trace the sequence of decisions and understand how the model arrives at a particular prediction. Moreover, the inverted tree structure allows us to visually assess the complexity and depth of the decision tree. A tree with many levels and branches indicates a more intricate decision-making process, while a shallow tree with few splits suggests a simpler model. This visual cue helps in understanding the model's complexity and potential for overfitting or underfitting. The graphical representation also facilitates the interpretation and communication of the decision tree's logic. Stakeholders, even those without a deep technical background, can easily grasp the flow of decisions by examining the tree structure. This transparency enhances trust in the model and enables meaningful discussions and collaborations between domain experts and data scientists. It's worth noting that while the inverted tree representation is the most common, there are variations in how decision trees can be visually depicted. Some representations may use different colors, shapes, or annotation to convey additional information, such as the impurity measures or feature importances at each node. In summary, the graphical representation of decision trees as inverted trees provides a powerful and intuitive way to understand and interpret the decision-making process. By starting at the root and following the branches until reaching the leaf nodes, we can trace the path of decision and gain insights into how the model arrives at its prediction. This visual representation enhances the interpretability and communication of decision trees, making them a valuable tool for both technical and non-technical audiences alike. Building a decision tree is a systematic process that involves two key steps: initial construction and pruning. These steps work together to create a model that effectively captures the underlying patterns in the data and makes accurate predictions. Initial construction. The initial construction phase is where the magic begins. The goal is to create a tree structure that splits the data into meaningful subsets based on the available features. The algorithm starts by selecting the most informative feature to make the first split. This feature is chosen based on its ability to separate the classes or reduce the impurity of the resulting subsets. Once the first split is made, we traverse down the branches of the decision node. Each branch represents a different outcome or condition based on the selected feature. We then assess the data points that fall into each branch. If all the data points belong to the same class, we have reached a leaf node, and the branch is considered pure. In this case, we can stop splitting and assign the majority class as the prediction for that leaf. However, if the data points within a branch still belong to different classes, we need to continue the splitting process. We recursively apply the same procedure to each impure branch, selecting the next best feature to split the data further. This process continues until all branches lead to leaf nodes, or until a predefined stopping criterion is met, such as reaching a maximum depth or a minimum number of samples per leaf. As we progress through the initial construction phase, the decision tree grows deeper and more complex. Each level of the tree represents a different combination of features and conditions, allowing the model to capture intricate relationships in the data. Pruning. Once the initial construction is complete, we have a fully grown decision tree. However, this tree may be overly complex and prone to overfitting. Overfitting occurs when the model becomes too specific to the training data and fails to generalize well to unseen data. This is where the pruning step comes into play. Pruning is the process of removing branches that are not useful for classification. The goal is to simplify the tree structure while maintaining its predictive power. By eliminating unnecessary complexity, pruning helps to reduce overfitting and improve the model's generalization ability. There are different approaches to pruning, such as pre-pruning and post-pruning. Pre-pruning involves setting stopping criteria during the initial construction phase to prevent the tree from growing too deep. This can include setting a maximum depth, a minimum number of samples per leaf, or a threshold for the impurity measure. Post-pruning, on the other hand, is performed after the initial construction is complete. It involves evaluating the impact of removing each branch on the model's performance. If removing a branch does not significantly degrade the model's accuracy, it can be pruned away. This process is repeated iteratively until the desired level of simplicity is achieved. The pruning step strikes a balance between model complexity and generalization. By removing unnecessary branches, we create a more compact and interpretable decision tree that is less likely to overfit the training data. It's important to note that the construction and pruning steps are not always performed in a strict sequential manner. Some algorithms, such as CART, classification and regression trees, combine the construction and pruning steps into a single optimization process. These algorithms use techniques like cost complexity pruning to find the optimal tree structure that maximizes accuracy while minimizing complexity. In conclusion, the construction of decision trees involves an initial phase of recursively splitting the data based on informative features, followed by a pruning phase to simplify the tree structure and prevent overfitting. By carefully selecting features, traversing branches, and pruning unnecessary complexity, we can build decision trees that are both accurate and interpretable. The resulting model provides a powerful tool for making predictions and understanding the underlying patterns in the data. At the heart of the decision tree algorithm lies the process of partitioning the dataset. This process follows a divide and conquer approach, also known as recursive partitioning. The goal is to create subsets of the data that are as homogeneous as possible with respect to the target variable. The partitioning process begins at the root of the tree, where the entire data set is considered. The algorithm then evaluates each available variable and determines the best split point to create the most homogeneous subsets. This decision is made based on a specific criterion, such as information gain or the Gini index, which measures the purity or impurity of the resulting partitions. The splitting process continues recursively for each resulting subset. The algorithm applies the same evaluation and decision-making process to each subset, considering the remaining variables and potential split points. This recursive partitioning continues until one of the following conditions is met. No more variables are available for splitting. No more observations are left in a subset. Further partitioning does not improve the homogeneity of the subsets. At each splitting step, the algorithm makes a greedy decision, considering only the current step and choosing the best variable and split point based on the immediate gain in homogeneity. This greedy approach means that the algorithm does not consider the global optimality of the entire tree, but rather focuses on making the best decision at each local step. Several algorithms have been developed for decision tree construction, each with its own criteria for evaluating the quality of splits. Two popular algorithms are ID3 and C4. 5, which use information gain as the splitting criterion. Another widely used algorithm is CART, classification and regression trees, which employs the Gini index to measure the impurity of the subsets. The specific splitting decision depends on the type of variable being considered and the desired split type. For nominal variables, two common approaches are binary splits and multi-way splits. In a binary split, the variable is divided into two subsets based on an optimal partitioning. On the other hand, a multi-way split creates as many partitions as there are distinct categories for the nominal variable. When dealing with continuous variables, the algorithm needs to determine the best cut point to create the most homogeneous subsets. One approach is to consider all possible splits and find the best cut point based on the chosen criterion. However, this can be computationally intensive, especially for large datasets. An alternative approach is to discretize the continuous variable into ordinal categories, effectively transforming it into a nominal variable. It's important to note that the decision tree algorithm is sensitive to the choice of splitting criterion and the handling of variable types. Different algorithms and approaches may yield different tree structures and performance. Therefore, it's crucial to carefully consider the characteristics of the dataset and the specific problem at hand when selecting the appropriate algorithm and splitting strategies. In summary, the partitioning process in decision tree algorithms follows a divide and conquer approach, recursively splitting the dataset into more homogeneous subsets based on the available variables and split points. The algorithm makes greedy decisions at each step, aiming to maximize the immediate gain in homogeneity. Different algorithms such as ID3, C4, 5, and CART employ various criteria to evaluate the quality of splits. The splitting decision also depends on the type of variable being considered, whether it is nominal or continuous, and the desired split type. By carefully navigating through these choices and considerations, decision tree algorithms can effectively partition the dataset and create a meaningful tree structure for classification or regression tasks. When working with decision trees, one of the key challenges is to strike the right balance between capturing the underlying patterns in the data and avoiding overfitting. Overfitting is a common pitfall that occurs when the tree becomes too complex, with an excessive number of branches that attempt to reflect every detail and outlier in the training set. Imagine a decision tree as a map that guides us through the decision-making process. An overfitted tree is like a map that is so detailed that it includes every tiny street, alleyway, and individual house. While such a map might be perfect for navigating a specific neighborhood, it becomes cumbersome and impractical when trying to navigate an entire city or region. Similarly, an overfitted decision tree may perform exceptionally well on the training data, as it has learned to memorize every nuance and peculiarity. However, when presented with new, unseen examples, an overfitted tree often struggles to generalize effectively. It becomes overly sensitive to the noise and idiosyncrasies present in the training set, leading to poor accuracy in classifying unknown instances. To mitigate the risk of overfitting, two common approaches are employed: pre-pruning and post-pruning. Pre-pruning, also known as early stopping, involves halting the tree construction process before it reaches its full depth. By setting certain criteria, such as a maximum depth threshold or a minimum number of instances per leaf, we can prevent a tree from growing too complex. This approach aims to find a sweet spot where the tree captures the essential patterns in the data without delving into the minute details that may lead to overfitting. On the other hand, post-pruning takes a different approach. Instead of stopping the tree construction early, post-pruning allows the tree to grow to its full extent, capturing all the intricate patterns in the training data. Once the tree is fully built, a pruning process is applied to remove the branches that are deemed unnecessary or detrimental to the tree's generalization ability. The post-pruning process involves evaluating the impact of removing each branch on the tree's performance. If the removal of a branch does not significantly degrade the accuracy of the tree, it can be pruned away. This process is repeated iteratively, gradually simplifying the tree structure while maintaining its predictive power. By eliminating the overly specific branches, post-pruning helps to create a more robust and generalizable tree. The choice between pre-pruning and post-pruning depends on various factors, such as the size and complexity of the dataset, the computational resources available, and the specific requirements of the problem at hand. Pre-pruning is often preferred when dealing with large datasets or when computational efficiency is a priority. It allows for faster tree construction and can prevent the tree from becoming excessively deep. However, pre-pruning may sometimes result in underfitting, where the tree fails to capture important patterns in the data. Post-pruning, on the other hand, is more computationally intensive, but offers a more fine-grained control over the tree's complexity. By allowing the tree to grow fully and then selectively pruning the branches, post-pruning can often lead to better generalization performance. It provides a more comprehensive exploration of the feature space and can capture subtle patterns that may be missed by pre-pruning. In practice, a combination of both pre-pruning and post-pruning techniques can be employed to strike a balance between model complexity and generalization ability. By carefully tuning the pruning parameters and monitoring the tree's performance on validation data, data scientists can find the optimal level of simplification that maximizes the tree's accuracy while avoiding overfitting. In conclusion, overfitting is a common challenge in decision tree learning, where the tree becomes overly complex and fails to generalize well to unseen data. To combat overfitting, pre-pruning and post-pruning techniques are employed. Pre-pruning stops the tree construction early based on predefined criteria, while post-pruning removes unnecessary branches after the tree is fully built. By applying these pruning methods judiciously, decision trees can be optimized to capture the essential patterns in the data, while maintaining their ability to make accurate predictions on new, unknown examples. Decision trees have emerged as a popular and versatile tool in the field of machine learning, offering a range of advantages while also presenting certain limitations. Let's explore the strengths and weaknesses of decision trees to gain a comprehensive understanding of their capabilities and potential drawbacks. Pros. One of the most significant advantages of decision trees is their computational efficiency. Building a decision tree is relatively cheap in terms of computational resources, making them suitable for large datasets and real-time applications. The tree construction process can be performed quickly, even on modest hardware, without requiring extensive computational power. Another key strength of decision trees is their interpretability. Unlike some black box models, decision trees provide a transparent and easily understandable representation of the decision-making process. The tree structure, with its hierarchical arrangement of nodes and branches, can be readily interpreted by humans. This interpretability is particularly valuable in domains where understanding the reasoning behind predictions is crucial, such as healthcare, finance, and legal applications. Decision trees also excel in handling missing values and irrelevant features. When constructing a tree, the algorithm can effectively handle instances with missing data points by considering alternative paths or using surrogate splits. This robustness to missing values is particularly useful in real-world scenarios where data may be incomplete or noisy. Additionally, Decision trees have the ability to identify and ignore irrelevant features during the tree construction process. By selecting only the most informative features at each split, decision trees can focus on the key attributes that contribute to the target variable, disregarding the noise. Cons. Despite their numerous advantages, decision trees also have several limitations that should be considered. One of the primary concerns is their propensity to overfit the training data. Overfitting occurs when the tree becomes too complex, capturing noise and idiosyncrasies specific to the training set. An overfitted tree may exhibit excellent performance on the training data, but fail to generalize well to unseen examples. This can lead to poor predictive accuracy when applied to new data. Another potential issue with decision trees is the risk of biased trees when dealing with imbalanced class distributions. If certain classes dominate the training data, the tree may be biased towards those classes, leading to suboptimal performance on minority classes. This bias can be particularly problematic in applications where accurate prediction of rare events or minority classes is crucial, such as fraud detection or medical diagnosis. Decision trees can also be sensitive to variations in the training data. Small changes or perturbation in the data can sometimes result in significantly different tree structures. This instability can be attributed to the greedy nature of the tree construction process, where each split is determined based on the current subset of data. Consequently, decision trees may exhibit high variance and be prone to overfitting, especially when dealing with noisy or high-dimensional datasets. Lastly, decision trees often suffer from relatively low accuracy compared to more sophisticated machine learning algorithms. While they can capture simple and interpretable decision rules, decision trees may struggle to model complex relationships and interactions among features. In many cases, ensemble methods such as random forest or gradient boosting, which combine multiple decision trees, can significantly improve predictive performance by leveraging the collective power of multiple models. In conclusion, decision trees offer a range of advantages, including computational efficiency, interpretability, and the ability to handle missing values and irrelevant features. However, they also present challenges such as overfitting, bias towards dominant classes, instability, and relatively low accuracy. To mitigate these limitations, techniques such as pruning, ensemble methods, and careful model selection and evaluation should be employed. By understanding the strengths and weaknesses of decision trees, data scientists can make informed decisions on when and how to leverage this powerful tool in their machine learning projects. In the realm of machine learning, decision trees have proven to be a powerful and intuitive tool for solving a wide range of problems. However, a single decision tree often faces limitation in terms of simplicity or specificity. It may struggle to capture complex relationships or generalize well to unseen data. This is where ensemble learning comes into play, offering a promising approach to overcome the shortcomings of individual decision trees. Ensemble learning is based on the idea that many models, even if they are considered weak learners, can work together to achieve better performance than a single model. It draws inspiration from the concept of collective intelligence, where a group of experts reaches a consensus decision on an issue. Just as the collective wisdom of a diverse group of experts often outperforms the judgment of a single authority, ensemble learning leverages the combined power of multiple models to make more accurate and robust predictions. In the context of decision trees, ensemble learning algorithms such as boosting, bagging, and random forest have gained significant popularity. These techniques harness the strength of multiple decision trees by training them on different subsets of the data, or by introducing randomness in the tree construction process. Boosting is an iterative ensemble method that focuses on training a sequence of weak learners, each attempting to correct the mistakes made by the previous learners. The weak learners are typically shallow decision trees, also known as decision stumps. In each iteration, the algorithm assigns higher weights to the misclassified instances, forcing subsequent learners to focus on the challenging samples. The final prediction is obtained by combining the outputs of all the weak learners, giving more weight to the learners that perform better. Gradient boosting machines, GBM, and AdaBoost are popular boosting algorithms that have shown remarkable success in various domains. Bagging, short for bootstrap aggregating, takes a different approach to ensemble learning. Instead of iteratively training weak learners, bagging involves training multiple decision trees independently on random subsets of the training data. Each tree is built using a bootstrap sample, which is obtained by randomly sampling the original dataset with replacement. The final prediction is determined by aggregating the outputs of all the trees, typically through majority voting for classification tasks or averaging for regression tasks. Bagging helps to reduce overfitting and improve the stability and accuracy of the ensemble model. Random forest is an extension of the bagging technique that introduces an additional layer of randomness in the tree construction process. In addition to training each tree on a bootstrap sample of the data, random forest also randomly selects a subset of features at each split point. This random feature selection helps to decorrelate the trees and reduce their tendency to focus on the same dominant features. By introducing diversity among the trees, random forest aims to improve the overall performance and robustness of the ensemble. One of the key advantages of ensemble learning is its ability to handle the uncertainty and variability that often arise when building a single decision tree. In many cases, there may be little difference in choosing between alternative variables or split points during the tree construction process. Ensemble methods embrace this uncertainty by allowing different trees to explore different paths and make different decisions. The diversity among the trees helps to capture a wider range of patterns and relationships in the data, leading to improved generalization and reduced overfitting. Moreover, ensemble learning techniques offer the flexibility to balance the bias-variance trade-off. By combining multiple models, ensemble methods can reduce the variance associated with individual trees while maintaining a relatively low bias. This is particularly beneficial when dealing with complex data sets or when the underlying relationships are not easily captured by a single tree. In conclusion, ensemble learning has revolutionized the field of machine learning by demonstrating the power of combining multiple models to achieve superior performance. By leveraging techniques such as boosting, bagging, and random forest, data scientists can harness the collective intelligence of decision trees to tackle complex problems and make more accurate and robust predictions. Ensemble learning not only addresses the limitation of individual decision trees, but also provides a framework for handling uncertainty, reducing overfitting, and improving generalization. As we continue to explore the vast potential of ensemble learning, we can expect to see even more innovative applications and breakthroughs in various domains, from healthcare and finance to natural language processing and computer vision. In the world of machine learning, decision trees have emerged as a powerful and intuitive tool for solving a wide range of problems. However, unlike low variance models such as regression, decision trees are known to have high variance. This means that small changes in the training data can lead to significantly different tree structures and predictions. To mitigate this shortcoming and improve the stability and accuracy of decision tree models, a technique called bootstrap aggregation, or bagging, has gained prominence. Bagging is based on a fundamental principle in statistics. Averaging reduces variance. By creating multiple versions of a model and combining their predictions, we can effectively reduce the overall variance and improve the robustness of the final model. In the context of decision trees, bagging involves drawing bootstrap samples from the original dataset and training a separate tree on each sample. A bootstrap sample is created by randomly selecting observations from the original dataset with replacement. This means that some observation may appear multiple times in a bootstrap sample, while others may be omitted entirely. By training decision trees on these bootstrap samples, we introduce diversity and randomness into the learning process. Each tree is grown deep without pruning, resulting in models with high variance but low bias. Once the individual trees are trained, the bagging algorithm combines their prediction to make the final prediction. For regression problems, the predictions of all the trees are averaged to obtain the bagged prediction. For classification problems, where the response variable is qualitative, bagging employs a majority voting scheme. Each tree in the ensemble predicts the class label for a given input, and the class with the most votes across all the trees is selected as the final prediction. One of the advantages of bagging is that it provides a built-in way to measure the accuracy of the ensemble model without the need for a separate cross-validation procedure. This is achieved through the concept of out-of-bag, OOB error. When creating bootstrap samples, approximately 1/3 of the observations are left out of each sample. These observations, known as OOB observations, can be used to assess the performance of the bagged model. For each observation in the original dataset, we can obtain predictions from the trees that did not include that observation in their bootstrap sample. On average, each observation will be an OOB observation in 1/3 of the trees. By aggregating the predictions of these trees, either through averaging for regression or majority voting for classification, we can calculate the OOB prediction for each observation. The overall OOB error is then computed by comparing the OOB predictions with the actual values of the response variable. The OOB error provides an unbiased estimate of the ensemble model's performance, as it uses observations that were not used in the training process. This eliminates the need for a separate validation set or cross-validation procedure, making bagging computationally efficient and straightforward to implement. In summary, bagging is a powerful ensemble technique that addresses the high variance problem of decision trees. By creating multiple bootstrap samples, training trees on each sample, and combining their predictions, bagging reduces the overall variance and improves the stability and accuracy of the model. The OOB error provides a convenient way to assess the performance of the bagged model without the need for additional validation procedures. Bagging has proven to be effective in a wide range of applications, from regression and classification tasks to feature selection and anomaly detection. As we continue to explore the potential of ensemble learning, bagging remains a fundamental tool in the data scientist toolkit, enabling us to harness the power of multiple models to solve complex problems and make more accurate and robust predictions. While bagging offers significant advantages in terms of reducing variance and improving the accuracy of decision tree models, it also introduces a challenge in terms of model interpretation. Unlike a single decision tree, where the importance of each variable can be easily assessed by examining the tree structure, bagging involves multiple trees, each trained on a different bootstrap sample. This makes it less straightforward to determine the overall importance of the variables in the ensemble model. However, bagging provides a powerful technique to assess variable importance by leveraging the Gini index, or RSS, for regression problems. The Gini index is a measure of impurity or inequality used in decision tree splitting. It quantifies the degree of heterogeneity within a node and helps determine the best split at each step of the tree building process. To determine the overall importance of a variable in a bagged model, we can calculate the total amount by which the Gini index has decreased due to splits over that particular variable, averaged over all the trees in the ensemble. This process involves the following steps. For each tree in the bagged model, we traverse through the tree structure and identify the splits that involve the variable of interest. At each split, we calculate the decrease in the Gini index resulting from that split. This decrease represents the improvement in the purity of the resulting child nodes compared to the parent node. We sum up the decreases in the Gini index across all the splits involving the variable of interest within each tree. Finally, we average the total decrease in the Gini index for the variable across all the trees in the ensemble. The resulting value represents the overall importance of the variable in the bagged model. Variables with higher average decrease in the Gini index are considered more important, as they contribute more to the overall purity and separation of the classes or the reduction of impurity in the ensemble. This variable importance measure provides valuable insights into the relative influence of each predictor in the bagged model. It allows us to identify the variables that have the greatest impact on the model's predictions and can guide feature selection and model interpretation. For example, consider a bagged model trained on a dataset with multiple predictors. By calculating the variable importance using the Gini index, we may discover that certain variables consistently appear at the top splits of the trees and contribute significantly to the reduction of impurity. These variables can be considered as the most influential predictors in the model. On the other hand, variables with low importance scores may have limited impact on the model's predictions and could potentially be removed or replaced without significantly affecting the model's performance. This information can be valuable in simplifying the model, reducing computational complexity, and improving interpretability. It's important to note that the variable importance measure based on the Gini index is specific to the bagged model and may differ from the importance rankings obtained from a single decision tree. The bagging process introduces randomness and diversity among the trees, which can lead to different variable importance rankings compared to a single tree. Moreover, the variable importance measure should be interpreted in the context of that specific problem and dataset. It provides a relative ranking of the variables within the bagged model, but does not necessarily imply causality or guarantee that the top-ranked variables are the most important in a broader sense. In conclusion, while bagging introduces complexity in model interpretation due to the presence of multiple trees, the variable importance measure based on the Gini index provides a valuable tool for assessing the overall influence of each predictor in the ensemble model. By calculating the average decrease in the Gini index across all the trees, we can identify the variables that contribute most to the model's predictions and gain insights into their relative importance. This information can guide feature selection, model simplification, and interpretation, enabling us to build more accurate and interpretable bagged models. While bagging has proven to be an effective technique for reducing variance and improving the accuracy of decision tree models, there is still room for further enhancement. One of the challenges in bagging is that the decision tree algorithm tends to favor stronger predictors, which can lead to the construction of identical or highly correlated trees. This correlation among the trees can limit the effectiveness of bagging in reducing variance. In the traditional bagging approach, all available variables are used to construct each bagged tree. The decision tree algorithm, by nature, selects the most informative variables at each split, aiming to maximize the reduction in impurity or minimize the error. As a result, the stronger predictors are more likely to be chosen repeatedly across different trees, leading to similar tree structures and correlated predictions. The issue with having correlated trees is that averaging their predictions may not result in a substantial reduction of variance. The purpose of averaging in bagging is to cancel out the individual errors and fluctuation of the trees, thereby stabilizing the final prediction. However, when the trees are highly correlated, their errors tend to be in the same direction, and averaging them may not effectively neutralize the errors. To address this limitation and further improve the performance of the bagged ensemble model, it is crucial to introduce mechanisms that promote diversity among the trees. By decorrelating the bagged trees, we can ensure that each tree provides a unique perspective and contributes meaningfully to the final prediction. One effective approach to decorrelate the bagged trees is to introduce randomness in the variable selection process. Instead of using all available variables at each split, we can randomly select a subset of variables for consideration. This technique, known as random feature selection or random subspace method, encourages each tree to focus on different sets of variables, leading to more diverse tree structures. By limiting the number of variables considered at each split, we reduce the likelihood of the same strong predictors being selected repeatedly across all trees. This promotes the inclusion of weaker predictors that may have been overshadowed by the stronger ones in the traditional bagging approach. The randomness introduced in the variable selection process helps to break the correlation among the trees and enhances the ensemble's ability to capture a wider range of patterns and relationships in the data. Another technique to promote diversity among the bagged trees is to introduce randomness in the sample selection process. Instead of using the same bootstrap sample for all trees, we can create unique bootstrap samples for each tree. This ensures that each tree is trained on a slightly different subset of the data, further reducing the correlation among the trees. The combination of random feature selection and unique bootstrap sampling creates an ensemble of diverse and decorrelated trees. Each tree in the ensemble provides a distinct perspective on the data, capturing different patterns and relationships. By averaging the prediction of these diverse trees, we can achieve a more effective reduction of variance and improve the overall performance of the bagged model. It's important to note that the optimal number of variables to consider at each split and the size of the bootstrap samples may vary depending on the specific problem and dataset. These hyperparameters can be tuned through techniques such as cross-validation to find the best balance between diversity and accuracy. In addition to random feature selection and unique bootstrap sampling, other techniques such as random forests and extremely randomized trees further enhance the diversity and performance of bagged models. These methods introduce additional layers of randomness in the tree construction process, such as randomly selecting split points or using random thresholds for continuous variables. In conclusion, while bagging is a powerful technique for reducing variance and improving the accuracy of decision tree models, the presence of correlated trees can limit its effectiveness. By introducing mechanisms to decorrelate the bagged trees, such as random feature selection and unique bootstrap sampling, we can promote diversity among the trees and enhance the ensemble's ability to capture a wider range of patterns and relationships in the data. These improvements lead to more effective variance reduction and better overall performance of the bagged model. As we continue to explore and refine these techniques, we can unlock the full potential of bagging and build more accurate and robust ensemble models. Random forest is a powerful ensemble learning technique that builds upon the principles of bagging to create a more diverse and robust set of decision trees. While bagging focuses on sampling observations to create multiple trees, random forest takes it a step further by introducing an additional layer of randomness in the variable selection process. In a random forest, we not only sample the observations through bootstrap sampling, but also sample the variables at each split of the bagged trees. This means that at each node of a tree, instead of considering all available variables for splitting, we randomly select a subset of variables to evaluate. The size of this subset is a hyperparameter of the random forest algorithm. The purpose of sampling the variables at each split is to force the algorithm to consider only a small number of predictors at a time. By restricting the number of variables available for splitting, we give a chance for weaker variables to be included in the tree construction process. This is particularly beneficial when dealing with data sets that have a large number of variables, some of which may be highly correlated or have a strong influence on the target variable. The impact of sampling the variables becomes evident when we consider the likelihood of a strong predictor being included in each split. By using a subset of variables at each split, we introduce randomness and diversity in the tree construction process. This allows weaker variables to have a greater influence on the tree construction and can lead to the discovery of important interactions and patterns that may have been overlooked in a traditional bagging approach. It's worth noting that bagging can be seen as a special case of random forest, where all available variables are used at each split. However, By introducing the variable sampling step, random forest extends bagging and creates a more diverse and robust ensemble of trees. The benefits of random forests are numerous. By combining bootstrap sampling of observations with random variable selection at each split, random forest effectively decorrelates the trees and reduces the impact of highly correlated or dominant variables. This leads to a more balanced and diverse set of trees, each capturing different aspects and patterns in the data. Moreover, random forest is known for its ability to handle high-dimensional datasets and its robustness to noise and outliers. The randomness introduced in the variable selection process helps to mitigate the impact of irrelevant or noisy variables, as they are less likely to be consistently selected across multiple trees. Another advantage of random forest is its built-in feature importance measure. By aggregating the importance scores of each variable across all the trees in the ensemble, random forest provides insights into the relative contribution of each variable to the overall prediction. This can be valuable for feature selection, model interpretation, and gaining a deeper understanding of the underlying data. In conclusion, random forest is a powerful extension of bagging that introduces an additional layer of randomness in the variable selection process. By sampling both observation and variables at each split, random forest creates a diverse and robust ensemble of trees that can capture complex patterns and relationships in the data. The hyperparameter controlling the number of variables considered at each split plays a crucial role in balancing diversity and accuracy. With its ability to handle high-dimensional datasets, robustness to noise, and built-in feature importance measures, random forest has become a go-to technique for many machine learning tasks, including classification, regression, and anomaly detection. As we conclude this lesson, I want to express my genuine hope that you found the material both informative and engaging. It has been a pleasure presenting this content to you, and I sincerely wish you all the best in your future endeavors. Thank you for your attention and participation.